Welcome to the new features presentation for Lucidshape Caa version 2022.3. The main chapters of this presentation are the base module enhancements, the macrofocal freeform designer lens, and the light guide design module enhancements. Let us begin with the base module enhancements. Here we have major additions to the advanced analysis tool, a new license plate sensor, an automatic aiming option for the test tables, the dynamic ray trace surface filter, simulation enhancements, and the Catia V5-6R support. The Advanced Analysis tool received the following updates: a bird's eye view and a driver view, an isoline comparison feature, over 60 new measurement functions, the option to import Lucidshape LUG regulation test tables, measurement value derating, requirement margin, and location re-aiming features. Customizable measurement tables with a 3-layer hierarchy, enhanced Excel export reproducing the 3-layer hierarchy, and luminance image tone mapping, including human eye vision image. Before we go into the details, let us take a look at the advantages in a nutshell. You have now user-defined and automated analysis procedures, which will save dozens of engineering hours in every project. You get access to the Lucidshape library of over 1000 regulation test tables. There is now the option for measurement value derating, requirement margin, and location re-aiming features, allowing for best-in-practice analysis. Furthermore, enhanced luminance image analysis features are available. One of the special views available is the bird's eye view to analyze the road illumination performance. Another special view is the driver view. You can use it to visualize the road illumination as observed by the driver. Another new feature is the isoline overlay. You can visually compare light distributions by overlaying multiple sets of isolines, then using the legend to turn on and off specific isolines and to highlight them in the view. Lucidshape type measurement functions are a representation of the Lucidshape test table measurement functions, but inside advanced analysis. And I will go into more details later. You can access the functions via the analysis menu. We will find 5 submenus: lit measure points, lines, zones, bird's eye view, and miscellaneous. In the lit measure points section, you can measure one, multiple, or a matrix of points. Generally, the values are measured at the exact UV location by interpolating between neighboring cells. However, with lit measure point cell, the measurement of a cell value is also possible. Relative measurements are also possible. For example, measuring relative to a value at a certain position or measuring relative to a lid's maximum. In the lit measure lines section, you can scan a line for a maximum and minimum value. Lit measure line reports the maximum and minimum values on a line between 2 points, whereas lit measure max reports only the maximum. Relative measurements between 2 lines are also possible. You draw 2 lines, then the maximum and minimum of the first line are represented as percentage values of the maximum of the second line. In the lit measure zones section, you can scan areas or boundaries. For example, lit measure zone reports the maximum and minimum values of an area inside a UV zone, whereas lit measure zone flux reports the luminous flux of the area. Relative measurements are also possible. For example, in lit measure zone relative to max, the maximum and minimum values are expressed relative to the maximum of the entire lid. Lit measure max in zone checks if the lit maximum is inside the specified zone. Lit measure boundary functions are combined line measurements. They measure at the border of a specified zone. In the lit measure bird's eye view section, you can investigate bird's eye view illuminance plots. For example, lit measure lux range U reports the forward reach in meters from a specified illuminance requirement, e.g. 3 lux, whereas lit measure spread range V reports the coverage in meters at a given distance for a specified illuminance requirement. In the lit measure miscellaneous section, you can find measurement functions which did not fit into the other categories. For example, lit measure min reports the minimum value of the entire lid, whereas lit measure grad FMVSS reports the vertical gradient at a given horizontal position, and lit measure circle on license plate reports the mean value within a specified circle. At the beginning of an evaluation, we usually need to import the regulation test table. Here, the Advanced Analysis tool supports the direct import of Lucidshape LUG regulation test tables. Here's an example how such an imported Lucidshape test table would look like in Advanced Analysis. We will go through more of the details in later slides. For now, you can see the light distribution with visual feedback in the form of lines and points at the top, the 3-layer hierarchy table header in the middle, and the rows of measurements below that, including the pass and fail column. Advanced Analysis now offers a customizable 3-layer hierarchy table. The top layer consists of options, measurements, location, unit, requirements, results, margins, and assessments. In the measurement section, the parameters are as follows: the name of the measurement, followed by the type of the measurement function, for example, lit measure point. Then additional parameters, which are dependent on the function. After that, we have the re-aim option, which offers a location variance of definable size. Then we have the threshold option, which offers to exclude values outside a defined range. And finally, the derating option, where a variance to the measured value can be added. For the re-aim option, the location of a measurement point is varied within a defined rectangle. The nominal, minimum, and maximum values are reported. Let us take a look at an application example for the re-aim option. FMVSS 108 allows for a 1/4 degree re-aim in any direction to fulfill the requirement. In this example, we see a red rectangle in the light distribution indicating the re-aiming range for the point 0.86D 3.5L. In the graph, we can see the variance in intensity for the specified re-aim range. When using curve projections to evaluate light distributions along a curve, it is common that the ends exhibit regions of little light. The min threshold can help here by ignoring such regions as shown in the red rectangle. For intermediate design iterations, engineers tend to work with the least number of rays possible. Max threshold can help by ignoring outliers caused by noise, especially in luminance distributions. The derating option allows the user to assess a light distribution for compliance to requirements over a flux range, as the regulation must be met over the entire flux range. For this reason, engineers calculate an aggregate min-max derating that must be checked during photometric testing. The test is then performed for minimum, nominal, and maximum derating conditions. The derating is given as a scaling factor. For example, 0.8 means 80% of nominal value. There are multiple causes for flux variations, including LED brightness groups, thermal dependence of LED flux, material variations, and LED drivers. In the graph to the right, we can see the change in luminous flux over temperature. In the table, we see multiple brightness groups with varying flux. In the requirements section, you can define minimum and maximum values to evaluate the measurements against. Some measurements allow you to have more control, In that case, this is specified in the quantity section. For example, a mean value evaluation. The custom sections allows for in-house measurement value criterion. In this example, the in-house criterion is the minimum intensity of 1100 candela. The results section provides the measured values. First we have the value. If you have re-aim, it consists out of the nominal, the re-aim min, and the re-aim max value. If you perform a scan, you have a minimum value, a maximum value, a flux, a mean, a median, and a variance. If there are 3 entries in any column, you're using derating. In the example to the right, one measurement point with re-aiming and min-max derating provides a total of 9 values. Many regulations allow an amount of fluctuation to pass. For a measurement to pass, the margin must be over 100%. These calculated margins are contained in the margins section. For the minimum regulation, you take the nominal value divided by the requirement multiplied by 100. For the maximum regulation, you take the requirement divided by the nominal value multiplied by 100. For the minimum custom, you take the same as the minimum regulation, except it uses the custom requirement. For the maximum custom, you take the same as the maximum regulation, except it uses the custom requirement. In this example, we have the requirements of 1000 candela and the custom criterion of 1100 candela. So the normal margin is 1450% without derating based on the 14,503 candela measured, and the custom margin is 1318%. The assessment section enables you to quickly view if your measurements are passing the requirements you have defined. If the item passes, a green checkmark displays. If the item fails, a red X displays. The minimum regulation section is evaluating against the regulation minimum. The maximum regulation section is evaluating against the regulation maximum. The composite regulation is the total result of the minimum and maximum regulation. Assessments for the custom criterion are available too. If any values fail, then the total value will fail. The measurement data grid contains a large amount of data that you may want to manipulate further outside of advanced analysis. You can export from and import data to advanced analysis from Microsoft Excel in several different ways. The commands in advanced analysis for exporting to Excel refer to Current tab and All tabs. This is referring to the currently active tab or all the tabs in the measurement data grid. When you run Export Analysis Results, the resulting spreadsheet contains 2 tabs, Test Table and Test Results. When you run Export Test Table. The resulting spreadsheet contains only the Test Table tab. This approach is used to re-import the table later. Test Table contains the values for all manipulation points in the measurement. Test Results contains the results for the measurement. Here is an Excel export example based on the data we used in advanced analysis. The spreadsheet contains quite a bit of data, so this slide is just to give you a first impression. Advanced analysis in Lucidshape Caa now offers a variety of tone mappers, including human eye vision image, in short yeehlee. There exist now two ways to access the tone mappers in Lucidshape Caa. The first way is to directly access the tools via the view properties or by launching yeehlee from the context menu of a light distribution. The second way uses the tone mappers inside the Advanced Analysis module. In the following slides, we're going through a quick example how to apply a yeehlee tone mapper. We begin by loading a luminance image in lit format. To do so, we simply select the File menu, open UV Data File, navigate to the example folder, and open the tower tail lamp lid. The following image appears quite dark. The cause for this is a linear display of the luminance data, which can span 7 or more orders of magnitude, while a regular LCD monitor can display only 2 orders of magnitude. Now we can access the Data Manager, which provides access to all tone mappers, including yeehlee. To do so, we go to the Datasets menu and select Manage Datasets. Then we add the default tone mapped image based on the lit file by right-clicking on Tower Tail Lamp Lid and then selecting Add Tone Mapped Image. After accepting the default name, we can see a new entry under Tone Mapped Images. By default, the tone mapper is set to linear. Other options are logarithmic, Mansell, OpenEXR, Reinhardt, and yeehlee. Since these tone mappers were already available, we will not go into details this time. To create the yeehlee image, we highlight Tone Mapped Image in the Data Manager, then select Human Eye Vision Image and click Apply. Note that you can resize the Data Manager dialog to access all parameters of the yeehlee tool. The new yeehlee image is created as a separate tab in Advanced Analysis. This allows for the creation of multiple tone-mapped images of the same source image. Note that the tone mapper only changes the appearance of luminance data on the screen. It does not change the luminance values itself. Therefore, measurements will produce the same results as on the source image. In this example, we use two luminance images of a taillight. One image only contains the light of the environment source, while the other only contains the light of the stop lamp. A group is created to combine both images, and then heavy is applied to all three images, the original two and the combined output. This heavy luminance image depicts the unlit appearance of the taillight. This heavy luminance image depicts the stop lamp lit appearance of the taillight. This heavy luminance image depicts the combination of environment source and stop lamp lit appearance of the taillight, forming a day scene. Since the lit appearance is difficult to see, we are going to scale down the environment source to create a night scene. In this example, a second group is formed, with the only difference being a reduction of the environment source luminance to 1% of the original value. This heavy luminance image depicts the combination of the reduced environment source and the stop lamp lit appearance of the taillight. This concludes the chapter of Advanced Analysis Improvements. We now come to a new feature, the license plate sensor. The feature offers an easy-to-use dialog to choose the fitting license plate for the project. Over 24 plate types are available, among them types for ECE, SAE and China GB. Regulation validation for license plate illumination is done in advanced analysis. Specific measurement functions and test tables are provided for this task. The next topic is the automatic aiming option for the test tables. When analyzing forward lighting systems, proper lamp aiming is required for meaningful results. Having an automated way of doing this is especially important during tolerance studies, when dealing with potentially thousands of light distributions. Our test table tool now offers a gradient detection algorithm to vertically shift the light distribution to the optimal position automatically. To the right, we see an example intensity distribution of an ECE low beam in false color and in true color mode. The arrows indicate how the algorithm would shift the light distribution. The test table dialog was enhanced with the automatic vertical aiming section. After activating the automatic aiming with a checkbox, we get access to the new parameters. Line at U sets the horizontal position for the vertical gradient scan. Target V sets the desired position of the cutoff line. meaning once the algorithm has found the cutoff line, it will shift it to target V and will display the shifted amount under Shift V. Test range defines the scan range in vertical direction, in this case from -3 to 3 degrees, and a delta step size of 0.1 degree. Let us take a look at an example using an ECE low beam. After opening the lid and the test table tool, we will select the correct regulation and check automatic vertical aiming. The tool requires the position of the cutoff line to be entered under target V. Since we might not know the exact position of the cutoff line, we are going to use a small trick to make our life easier. To do so, we set the vertical scan line to -2.5 degrees and click Apply. This ECE regulation performs a gradient check at -2.5 degrees. The gradient will be the highest at the cutoff line, which is usually at about -0.6 degrees vertically. For this reason, the value 0 seen at figure 1 for the vertical position verifies that the automatic shifting has been performed successfully. We read the value under Shift V, which is 0.6. This means the cutoff was found at -0.6 degrees and then was shifted by 0.6 degrees to 0 degrees, because that is what we specified at target V. Now we change the value under target V to -0.6, the verified position of the cutoff line. Of course, we can skip the previous steps if we know the position of the cutoff line already. After clicking Apply, we verify the vertical position value of the grade 2.5L, which is now -0.6, and also verify Shift V, which is now 0. After these steps, our calibration is complete, and we can use the Store button to save the settings in the model for later use. With the calibrated setup, we can now use the auto-aiming on a different lighting distribution. In this case, I have shifted the ECE low beam lid 0.8 degrees downwards. After clicking Apply, we see that the Shift V has changed to 0.8 degrees. So the algorithm has correctly detected the cutoff line and shifted the light distribution accordingly. Comparing the test result tables of the two lids, we can see that they are identical. Another sensor and analysis enhancement is the dynamic surface result filter. Optical designs often require the analysis of ray paths or photometry isolated for individual optical surfaces or a set of optical surfaces. Many of these simulations are computationally expensive, especially those related to signal lighting applications, including photorealistic images. The solution is a tool which allows you to perform the analysis in post-processing. The previous release introduced the surface result filter. It enables you to filter the simulated rays by the surfaces they interact with. In this release, the surface result filter is enhanced by a dynamic mode, which allows the filtering of the rays in post-processing. The Restore from Sensor dialog offers multiple modes of filtering. Restore ray path defined by UV region, restore ray path defined by surfaces, and restore lit defined by surface. When using multiple surfaces, a combination logic can be applied, such as the last surface a ray interacts with, any surface of a selection, all surfaces of a selection, or the negation of that selection. Here are the steps to use the dynamic surface filter. You configure a candela sensor with the ray history functionality and create a Monte Carlo simulation. Then create a surface result filter and associate the surface result filter with the sensor. Run the Monte Carlo simulation and then select the sensor ray history results from the specification tree to open the Restore from Sensor dialog. In this example, a solid PMMA circle prism was created with the light source inside the medium. The system was simulated in tri-stimulus color mode. After the simulation, one facet of the prism was selected in the Restore dialog. In this example, we take a look at the contribution of a single prism surface inside a light guide. With this release, we introduce two enhancements to the simulation engine. The first is that simulations now scale better with higher number of CPU cores. The second enhancement is related to the GPU trace. In the past, rays with thousands of reflections, for example in a light guide, would cause a slowdown in GPU trace simulations. With this release, a threshold option was introduced, which will terminate rays that fall below a certain luminous flux threshold. The result is a considerable speed increase for certain simulation situations. The next enhancement is the Catia V5-6R support. Lucidshape Caa 2022.3 now supports Catia V5-R31 and continues to support R27 to R30. As always, newer versions of Lucidshape Caa can read older versions, and higher revisions can read lower revisions, but not vice versa. This concludes the overview of the new features in the base module. We now come to the enhancements in the design module. This release introduces the FFD lens for MF design feature. Furthermore, a global shift UV parameter for the facet spread is now available. And the gap surfaces have now a flexible draft and dipole option. In this release, we expanded the freeform design feature from the macrofocal reflector to the macrofocal lens feature. The freeform design feature enhances the MF reflector and MF lens design capability by providing a more granular control over the light spread across the entire facet, which reduces the need to subdivide facets into multiple rows of facets. Now you can easily combine MF, torus, and FFD surfaces in one lens. Looking at the spread settings, the freeform design algorithm requires light intensity distribution data for a light target definition to calculate the correct facet shape. There are two ways of defining the desired light target distribution. FFD Simple uses the same approach as a macrofocal algorithm, where you define horizontal and vertical spreads. This is the best choice for a homogeneous and less structured light pattern. FFD plus lid. Here you directly provide a lid file as a light target. This is recommended for a more unique, complex structured light pattern. Let us take a look at an example. In this design, a lens with 8 FFD facets is created. Each facet uses its own input light distribution in the form of a letter, altogether forming the word synopsis. At the upper right, we see the intensity distribution. The result depicts 8 individual light contributions forming the word synopsis. To the lower right, we see the geometry of the lens. 8 facets loosely following the shape of an aspheric lens. The purple bezel is masking the stray light. Sometimes you need to shift the entire beam pattern left, right, or up, down. Previously, it was required to add the needed offset individually to each horizontal vertical spread parameter, which can be cumbersome when using many facets. The global shift UV option provides a more efficient and convenient solution for this task. In this example, a global shift of -5 degrees in U and V direction was applied in the MF spread dialog. After the simulation, we can see how the light distribution has been shifted accordingly. With this release, we introduce an optional dipole direction for macrofocal design features. When using this option, the draft angles specified in the gap parameters are measured relative to the dipole direction. To the right, you can see an MF reflector with an off-axis dipole direction indicated by the green arrow. The dipole direction override can be activated under Other Settings, General Switches, with extra dipole direction. A direction vector defines the dipole direction. The draft angle and height can be set under gap parameters as before. This chapter is about the enhancements to the Light Guide design module. More specifically, we have three sections: new analysis features, features added to the surface mode, and various other enhancements. The first section is about the new analysis features. Let us take a look at the new plots. This tab has always had individual bin intensity plots, but now has three others. Number 1, the normalized summed intensity, where all bins are summed together. Number 2, H-slice, through the scaled summed intensity. Number 3, V-slice, through the scaled summed intensity. You can set the V and H constant values, respectively, for the slices. Test points calculated from the scaled summed intensity can also be displayed, projected into the slice plane as red curves. Next is the Test Point tab, a table with the number, location, minimum and maximum values allowed. Additionally, you can see the scaled by scale factor value and the error estimate. The error estimate is very important. You need enough rays such that the error is low for the bins chosen. Here, the error is in the ±2% range, a Gaussian 1 minus sigma. Finally, we have the Load Points tab. Here, you can also load your own test points, or reload the default ECE DRL test points. The format is U, V, min, max on each line representing one test point. The next tool helps with the design of an efficient system. The Auto-Scale feature scales the intensity distribution to the number of lumens needed to just pass all non-zero test points. It provides a simple way to understand comparative efficiency of different designs. Percentage values of the peak for the H and V slices, at which LGDM will calculate the width of the slice. V value of the H slice and H value of the V slice can both be set to different values to look at different slices. The next section is about the new features added to the surface mode. The face curvature is now supported for east and west faces of surface mode prisms. The radius of the face can be accessed on the prism surface data, and Bezier tab. The Calculate Delimited Values feature on the Prism Surface tab samples the data in your system and returns a set of comma-delimited values in the fields that allow comma-delimited values. You can specify the number of delimited values returned. If the value is constant, only one number is returned. The X width to set spacing feature is now moved to the Bezier tab and can be used with the surface as well as the prism mode. After enabling the feature, use Create Prism Surface or Calculate Surface on the Prism Surface tab to use the feature, similar to the prism mode. The dipole feature found on the Options tab is now available for surface mode as well as prism mode. Optimization, Bezier tab, Bin Information tab, etc. show angles relative to the dipole direction as in prism mode. Prism Surface Data tab shows angles relative to the surface, always. The last section contains various other enhancements. When you create built-in cross-sections in LGDM, the parameters can now be changed directly in the profile's geoset later. This allows you to change profile parameters with a design table, for example. When using the feature of the previous slide, you may want to adjust the value of W in the profiles, which changes the width of the prism surface. Adjust Y width to match surface feature on prism tabs allows you to easily readjust the prism Y width in prism mode to match the changes you made in the prism surface. The radius spread feature on the Optimization Controls Main Controls tab allows you to add curvature based on spread angle to prisms interpolated over the bins in prism or surface mode. Improved bin weighting. During optimization, the Summary tab now shows the frozen value if you use a 0 weight to freeze the bin. Previously, it showed 0. Additionally, the weighting equation has been adjusted so that setting weights between 0 and 1 will give a smaller amount of change for the bin. It is time for the summary. The new release strengthens the Catia integrated design and development. You can accomplish all key tasks during an automotive lighting design on the same modeling platform. Major efficiency gains of the release are the advanced analysis capabilities, the freeform design lens, and the light guide design module enhancements. I'd like to thank you for taking the time to watch this presentation.